The English Channel is a formidable stretch of water. For centuries, it has stood as a natural moat between Great Britain and mainland Europe, a silver-gray ribbon separating two distinct cultures. It's not just a barrier, it's actually one of the busiest shipping lanes on the entire planet. Day and night, a constant procession of colossal container ships, ferries, and tankers navigates its often turbulent waters. This ceaseless traffic makes the channel a place of constant motion, a vital artery for global trade. The idea of crossing it has always been a fundamental part of life for the people living on its shores, but for most of history, that journey was at the mercy of wind, waves, and weather, a trip that could be both unpredictable and perilous. Despite its role as a divider, the channel has also inspired a powerful and persistent dream, the dream of a permanent connection. For over 200 years, long before the technology existed to make it a reality, visionaries, engineers, and even emperors imagined a way to cross this watery expanse without ever setting foot on a boat. They pictured a link that would defy the storms and the tides, a fixed path that would tie the island of Britain to the continent of Europe once and for all. This was more than just a practical idea about moving goods and people. It was a grand ambition to conquer a natural obstacle and, in doing so, to bring two nations closer together in a profound and unprecedented way. The desire for this connection was fueled by many things. There was the promise of faster, more reliable trade, allowing goods to flow freely without the delays caused by bad weather or the cumbersome process of loading and unloading ships. There was also the military consideration. A tunnel could, in theory, allow for the rapid movement of troops, a thought that brought both excitement and anxiety depending on the political climate of the time. Above all, though, there was the sheer human impulse to overcome a challenge, to look at a great natural barrier and say, "We can cross this." The dream of a tunnel was a testament to human ingenuity and the relentless desire to reshape the world to better suit our needs. This epic tale is not just about digging a hole, it's about turning a centuries-old fantasy into a concrete reality. It's the story of how engineers, politicians, and thousands of workers from two different countries came together to undertake one of the most audacious construction projects in human history. They faced immense geological dangers, financial risks, and the constant threat of failure deep beneath the seabed. The Channel Tunnel, or Chunnel, as it's affectionately known, is more than just a railway line under the sea. It's a monument to perseverance, a symbol of international cooperation, and a powerful reminder that with enough courage and cleverness, humanity can achieve the seemingly impossible. The very first serious proposal for a tunnel under the English Channel dates back to the dawn of the 19th century. In 1802, a French mining engineer named Albert Mathieu Favier presented a fantastical plan to Napoleon Bonaparte. His vision was not for a train, which had not yet been invented, but for a two-level tunnel through which horse-drawn carriages could travel. The upper tunnel would be for transport, illuminated by oil lamps, while the lower one would be for groundwater drainage. He even imagined a man-made island in the middle of the channel, a place where horses could be changed and passengers could take in the sea air. Though Napoleon was intrigued, the constant state of war between Britain and France meant the ambitious project never left the drawing board. As the century progressed, the Industrial Revolution brought steam power and with it, new and more practical dreams of a tunnel. The Victorian era was a time of immense engineering confidence, a period that saw the construction of incredible bridges, railways, and canals. In this climate of innovation, the idea of a channel tunnel was revived with vigor. Engineers like Aimé Thomé de Gamonde, a Frenchman who spent decades obsessively studying the channel's geology, conducted daring solo explorations of the seabed. He even proposed creating several artificial islands along the route to act as ventilation shafts and construction points. His detailed plans captured the public imagination and laid the scientific groundwork for future attempts. On the British side, Sir Edward Watkin, a visionary railway tycoon, became a passionate champion for the cause. In the 1880s, he began experimental tunneling, using an early version of a tunnel boring machine to dig from the cliffs near Dover. His machine successfully excavated over a mile of tunnel, proving that the chalky rock beneath the channel was indeed suitable for tunneling. For a brief moment, it seemed the dream was finally within reach. However, political and military fears in Britain began to mount. The press and prominent figures in the military warned that a tunnel would compromise the nation's island defenses, creating an easy invasion route for continental armies. These fears ultimately led the British government to halt the project, and Watkins' tunnel was abandoned. For nearly a century after Watkins' attempt, the tunnel idea remained dormant, a recurring but seemingly doomed ambition. It was discussed and debated, with new plans proposed after both World War I and World War II. But political hesitation and the sheer scale of the financial investment always proved to be insurmountable obstacles. The dream was kept alive only in the minds of a dedicated few. A grand what-if of modern engineering. It would take a profound shift in political will and a new era of European cooperation in the late 20th century to finally provide the right conditions for this 200-year-old dream to be resurrected from the pages of history and attempted for real. The success or failure of the Channel Tunnel hinged entirely on geology. For decades, geologists had studied the layers of rock that lay beneath the turbulent waters, searching for the perfect path. They knew that digging a tunnel 30 miles long under the immense pressure of the sea was an incredible risk. The wrong type of rock could lead to catastrophic flooding, structural collapse, and the complete failure of the project. The engineers were not just digging a hole, they were attempting to thread a needle through a complex and hidden landscape. A task that required immense precision and a deep understanding of the Earth itself. The entire project was a high-stakes gamble on the consistency of a single, specific layer of rock. The target for the tunnel was a very special layer known as the chalk marl. This geological formation was ideal for several reasons. Firstly, it was relatively soft and easy to dig through, which was crucial for the massive tunnel boring machines that would do the work. At the same time, it was strong enough to support the tunnel's structure without collapsing. Most importantly, the chalk marl is largely impermeable, meaning it does not allow water to pass through it easily. This quality was absolutely vital. It acted as a natural waterproof shield protecting the tunnel from the crushing weight of the sea above. Digging into the porous chalk layers above, or the water-bearing green sand below, would have been disastrous, inviting a flood that no pump could handle. Finding and staying within this specific layer was the project's greatest challenge. The chalk marl layer is not perfectly flat. It undulates like a ribbon, dipping and rising along its path between England and France. Before any digging could begin, an exhaustive geological survey was undertaken. Ships crisscrossed the channel, firing seismic charges and analyzing the echoes to create a detailed map of the seabed's hidden strata. Over 100 deep boreholes were drilled into the seabed to extract core samples, giving engineers a direct look at the rock they would have to conquer. This data was used to plot the tunnel's precise trajectory, a gentle downward slope from each coast meeting in the middle, carefully designed to remain within the protective embrace of the chalk marl. The risk was immense. Even with the best surveys, geology is never completely predictable. There was always the danger of encountering an unexpected fissure or a fault line in the rock, a geological anomaly that could suddenly allow seawater to pour into the tunnel. Such an event would not only be lethal for the workers caught in its path but could also doom the entire project, turning the partially dug tunnel into a permanent, water-filled tomb. The engineers and workers were essentially on a geological tightrope suspended between the solid earth below and the mighty sea above, with only a thin, carefully chosen layer of rock to keep them safe from disaster. For the Channel Tunnel to become a reality, it required more than just engineering genius. It demanded an unprecedented level of political and economic cooperation between Great Britain and France. For centuries, these two nations had been rivals, often engaged in conflict. The decision to finally link their lands was a momentous one, symbolizing a new era of partnership within Europe. In 1986, British Prime Minister Margaret Thatcher and French President François Mitterrand signed the Treaty of Canterbury, a landmark agreement that gave the official green light to the project. This treaty was not just a political document, it was a pact, a joint commitment to undertake one of the most challenging and expensive construction projects ever conceived. A crucial aspect of this agreement was the decision that the tunnel would be financed entirely by private investment. This was a massive risk. The governments of Britain and France provided the political framework and the legal authority, but they would not be providing the money. Instead, a consortium of banks and construction companies, forming a group called Eurotunnel, had to raise the billions of pounds needed to fund the project. This meant that the tunnel had to be commercially viable, it had to be built on time and on budget, and it had to attract enough passengers and freight to eventually pay back its investors. This added an intense layer of financial pressure to the already daunting engineering challenges. This joint venture required constant collaboration at every level. Two separate teams, one starting from Folkestone in England and the other from Coquelles in France, would dig towards each other with the aim of meeting in the middle. This meant that every decision, from the design of the tunnel boring machines to the safety protocols for the workers, had to be agreed upon by both sides. French and British engineers had to overcome language barriers and different engineering traditions to work as a single unified team. This spirit of cooperation was essential, as the success of the entire project depended on both sides working in perfect harmony, trusting each other's calculations and workmanship completely. The project was therefore a symbol of shared risk and shared ambition. If the tunnel failed, both nations would share in the colossal financial loss and the public embarrassment. But if it succeeded, they would share in the glory of having conquered the Channel and created a lasting monument to European unity. The sight of the Union Jack and the French tricolor flying side by side at the construction sites was a powerful visual representation of this new partnership. It was a declaration that these two historic nations were no longer separated by a narrow sea, but were now bound together by a common goal, their fortunes intertwined in a venture of steel, concrete, and sheer determination. At the heart of the Channel Tunnel's construction were 11 magnificent machines known as tunnel boring machines, or TBMs. These were not simply drills, they were mobile factories, complex steel behemoths, each stretching over 200 meters long and weighing more than 1,000 tons. The British and French teams used slightly different designs, but they all operated on the same basic principle. At the front of each TBM was a massive rotating cutting head, studded with tungsten-tipped steel teeth. This head would spin and grind its way through the chalk marl, chewing up the rock and pushing forward with immense hydraulic force. These mechanical moles were the workhorses of the project, tasked with the relentless job of carving out the tunnel deep beneath the sea. Operating a TBM was a complex and demanding process. As the cutting head advanced, the pulverized rock, mixed with water into a slurry, was transported backwards through the body of the machine, on a series of conveyor belts. It was then loaded onto small trains that ran along temporary tracks laid inside the newly dug tunnel, carrying the spoil back to the surface. At the same time, the rear of the TBM was responsible for building the tunnel itself. A giant robotic arm would pick up huge, curved segments of precast concrete from a carousel and meticulously place them into position, forming a complete ring. Once a ring was complete, the TBM would push off it using hydraulic rams to advance forward and begin cutting the next section. Life for the workers inside these machines was, honestly, incredibly tough and dangerous. They worked in shifts around the clock, in a noisy, cramped, and constantly moving environment. The heat generated by the machinery was intense, with temperatures often soaring above 35 degrees Celsius. The air pressure was kept artificially high in some sections to help prevent water from seeping in, which could lead to decompression sickness, a painful and potentially fatal condition. The constant threat of a sudden flood or a mechanical failure loomed over every shift. Is Daxomardi Stoudan, the men known as tunnel tigers, were a special breed, working under extreme conditions with skill and courage to keep the giant moles moving forward. The sheer scale of the excavation was staggering. On the British side, the spoil removed from the tunnels was used to create a whole new piece of land. Samphire Hoe, a 90-acre nature reserve, was built at the base of the Shakespeare Cliff near Dover, using nearly 5 million cubic meters of chalk, marl, excavated from beneath the channel. This turned a waste product of the construction into a lasting environmental asset. It stands as a physical testament to the immense volume of earth that was moved, meter by painstaking meter, by the relentless grinding of the tunnel-boring machines on their slow and steady journey towards France. Keeping the tunnels on the correct path was a task of almost unimaginable difficulty and importance. The British and French teams were digging towards each other from points over 30 miles apart, deep underground, with no line of sight. They had to meet in the middle, with a margin of error of just a few centimeters. A mistake in navigation could be catastrophic. If the tunnels missed each other, the project would be a failure. Worse still, if a tunnel veered out of the protective chalk marl layer, it could trigger a sudden and unstoppable inundation of seawater, with fatal consequences for the workers and the entire project. Precision was not just a goal, it was a matter of survival. To achieve this incredible accuracy, the engineers relied on a combination of traditional surveying techniques and cutting-edge technology. On the surface, surveyors used a network of satellites and fixed points on both coasts to establish an incredibly precise grid. This information was then transferred underground to the TBMs. Inside the tunnels, a sophisticated system of laser guidance was used to steer the machines. A laser beam was projected from a fixed point further back in the tunnel onto a target on the TBM. The machine's operator, guided by computer systems, had to constantly make minute adjustments to the TBM's direction and angle to keep the laser perfectly centered on the target, ensuring the tunnel followed the pre-planned route. Despite the advanced technology, the threat of water was ever present. The engineers knew they were tunneling under a sea that exerted immense pressure, and even the impermeable chalk, marl, was not perfect. In 1989, the British team faced a terrifying moment when their TBM hit a fissure in the rock. Water began pouring into the tunnel at an alarming rate, threatening to flood the machine and halt progress. The workers had to act quickly, drilling holes ahead of the TBM and pumping a specialized form of grout, a type of quick-setting concrete, into the fractured rock. This painstaking process sealed the fissure, allowing the TBM to advance safely, but it was a stark reminder of the constant danger they faced. The journey was a slow and nerve-wracking advance through the unknown. Every meter gained was a small victory against the immense forces of nature. The operators and engineers had to trust their instruments, their calculations, and their geological maps completely. They were navigating blind, steering a 1,000-ton machine through a hidden world, with the weight of the ocean above them and the fate of the entire project resting on their ability to stay on course. It was a testament to their skill and composure that they were able to maintain such an accurate path while battling heat, pressure, and the constant fear of what might lie in the rock just a few meters ahead. After 3 years of relentless digging, the moment the world had been waiting for was finally at hand. On 30th October 1990, the French and British TBMs digging the service tunnel, the smallest of the 3 tunnels, were just meters apart. The main TBMs were halted and a smaller probe was carefully drilled through the final wall of rock separating the 2 halves of the tunnel. A wave of air, the first to pass directly between Britain and France underground, rushed through the opening, a symbolic breath connecting the 2 nations. The air pressure on the French side was slightly higher, so it was French air that first flowed into the British tunnel. A small but significant detail in this historic moment, the final breakthrough, was a carefully orchestrated and highly emotional event. On 1st December 1990, 2 men, 1 British and 1 French, prepared to make history. Graham Fagg, a British tunneler, and Philippe Cosette, his French counterpart, were chosen to be the first to cross the newly opened gap. With the world's media watching via a live television link, they carefully widened the opening with hand tools until it was large enough to pass through. The first thing they did was reach through the hole and shake hands, a simple yet profoundly symbolic gesture that took place 100 meters beneath the English Channel. It was a handshake that represented the culmination of centuries of dreams and years of incredible effort. The precision of the engineering was nothing short of miraculous. When the surveyors checked the alignment, they found that the 2 tunnels met with a horizontal difference of just 35.8 centimeters and a vertical difference of only 5.8 centimeters. Over a distance of more than 30 miles, this was an astonishing feat of accuracy, a testament to the skill of the surveyors and the sophistication of the guidance systems. The handshake was not just a photo opportunity, it was a celebration of a near-perfect execution of an incredibly complex plan. It proved that the seemingly impossible task of meeting in the middle of a vast hidden underground space had been achieved. The breakthrough was a moment of immense pride and relief for everyone involved in the project. The thousands of workers on both sides had faced danger and difficulty for years, and this was their ultimate reward. The image of the 2 men, smiling and waving their national flags through the gap in the rock, became an iconic symbol of the project's success. It was a powerful message to the world that the physical barrier of the English Channel had finally been conquered. The 2 halves had become a whole, and the way was now clear to complete the final stages of the world's longest undersea tunnel. The dream had become a tangible reality, carved in chalk and concrete. Once the main running tunnels had broken through and the excavation work was complete, a significant question remained. What should be done with the colossal tunnel boring machines? These 11 mechanical giants had performed their task magnificently, but they were now deep underground, miles from where they had started. The cost and complexity of dismantling them piece by piece and transporting them all the way back to the surface would have been enormous. In the end, a more practical, if less glamorous fate was decided for most of these incredible machines. Their work was done, and their final journey would be a short one. Most of the TBMs were not brought back to the surface. Instead, they were steered off the main path of the tunnel and driven into specially excavated sidings or burial chambers carved into the rock. The valuable and reusable components, such as the main bearings, electronics, and hydraulic systems, were stripped from the machines and taken back to the surface. After being salvaged for parts, the huge steel bodies and the massive cutting heads of the TBMs were simply left behind, entombed in the very ground they had helped to conquer. They were then sealed off with concrete, becoming a permanent, hidden part of the tunnel's structure. This was a pragmatic solution born of engineering and economic necessity. The TBMs were designed for a one-way trip, built to dig forward, but not to reverse. To bring them back would have been a project almost as complex as the tunneling itself. Two of the smaller French TBMs were able to be dismantled and returned to the surface, but the larger, heavier British machines were simply too big and too far from the entrance to make retrieval a viable option. Their final resting place is deep beneath the sea, silent monuments to the incredible engineering effort that built the tunnel. This fate of the TBMs is a poignant final chapter in their story. These machines, which for years were the noisy, grinding heart of the project, now lie dormant in the darkness. They are the forgotten heroes of the Channel Tunnel, the mechanical moles that made the dream possible, now forever part of the landscape they created. For anyone traveling through the tunnel today, it is a fascinating thought that just a few meters away from the track, sealed behind a wall of concrete, lie the giant machines that carved the path, their mission complete and their steel bodies laid to rest in a tomb of chalk. The Channel Tunnel was officially opened by Queen Elizabeth II and President François Mitterrand on 6 May 1994. The final cost of the project had spiraled to over £9 billion, more than double the original estimate, a figure that created significant financial strain for the investors. Tragically, the project also came at a human cost. 11 workers, 10 of them British and 1 French, lost their lives during the construction, a somber reminder of the immense dangers involved in such a monumental undertaking. The chaos of the final years, marked by cost overruns and financial disputes, almost overshadowed the incredible technical achievement. But once the first trains began to run, the true legacy of the tunnel started to take shape. The tunnel's impact on travel between Britain and Europe was immediate and revolutionary. For the first time, passengers could board a train in the center of London and arrive in the heart of Paris or Brussels in just a couple of hours. Cars and lorries could be driven onto specially designed shuttle trains and transported under the channel in just 35 minutes, regardless of the weather. The tunnel transformed the geography of travel, making the journey to the continent faster, more reliable, and more convenient than ever before. It turned a full day's trip into a simple commute, binding the UK and mainland Europe closer than ever before. Safety was designed into every aspect of the tunnel. The system consists of 3 tunnels, 2 large running tunnels for the trains, and a smaller service tunnel in between. This service tunnel is a crucial part of the safety design, acting as an escape route in case of an emergency. Cross passages link the running tunnels to the service tunnel every 375 meters, allowing passengers to be evacuated quickly. A powerful ventilation system is designed to control smoke in the event of a fire, while a separate cooling system with pipes carrying chilled water runs the entire length of the tunnel to dissipate the heat generated by the high-speed trains. These systems make the Channel Tunnel one of the safest transport infrastructures in the world. Today, the Channel Tunnel stands as one of the 7 wonders of the modern world, a testament to what human beings can achieve when they combine bold vision with brilliant engineering and international cooperation. It is more than just a piece of infrastructure, it is a symbol of connection, overcoming a natural barrier that had defined history for thousands of years. The epic tale of its construction, from the early dreams of Napoleon's era to the final handshake under the sea, is a story of perseverance against incredible odds. It proves that even the most audacious of human ambitions can be realized, and that with courage and ingenuity, we can indeed reshape our world.